Hello again. In this video, we're going to go over section 2.6, which is about continuity. And we're going to start with the definition of continuity at a point. So a function f is continuous at a if the limit of f of x as x approaches a is equal to f evaluated at a. Okay, so I want to unpack this definition. On the left-hand side of this equation, this limit is really telling us what the y value of this function is getting closer to as x is getting closer to a. Now keep in mind, it's not telling us what the y value of the function is when x equals a. It's only telling us the y value of the function, what the y value of the function is getting closer to as x is getting closer to a. Now having said that, if the y value of this function is getting closer to the same y value that you get when x actually equals a, then that's when we say f is continuous at a. Okay, so that's what we mean by continuity at a point. Now there's really kind of three conditions that need to be satisfied in order for this limit to be equal to f evaluated at a. Obviously, both of these have to equal numbers. Okay, so f evaluated at a must be defined, and this limit must be defined, or the limit must exist. So in other words, f of a has to equal a number, and this limit has to equal a number. That's what the first two conditions here say. And then the third condition is whatever those numbers are, they have to be the same number, right? They have to be equal to each other. Okay, so that's called the continuity checklist. Now there's an important result that we can pull out of this definition of continuity at a. And if you remember, earlier we talked about using direct substitution to evaluate limits. And we said that there were, I guess, maybe three different cases where we could use direct substitution to evaluate limits, right? If the function were a continuous function, a linear function, or a polynomial, or a rational function, then we could use direct substitution to evaluate the limit of those functions. But now we can make a more general statement about when we can use direct substitution to evaluate the limit of a function. What we really need is we need the function to be continuous at a. And here's why. Because if f is continuous at a, then the limit of f of x as x approaches a must be equal to f evaluated at a by the definition of continuity at a. And that really means I can evaluate this limit on the left-hand side by simply substituting a into the function. In other words, direct substitution. And so this is a really nice result. We can now really say, when can we use direct substitution to evaluate a limit? And the answer is, we just need f to be continuous at a. If f is continuous at a, then I can evaluate this limit by simply plugging a into the function. And so that's a nice result. And so the reason we could use direct substitution to evaluate the limit of linear functions, polynomials, and rational functions is because they were continuous at that point a that the limit was that the x value was approaching in the limit. Okay, so I think this is what you should remember going forward. You know, to use direct substitution to evaluate a limit, you really just need f to be continuous at a, where a is the number that x is approaching in the limit. Okay. Okay, so having said that, Sometimes we use this word discontinuity at A, and when we use the word discontinuity at A, what we mean is f is not continuous at A. So we're going to use that term when a function is not continuous at A. We're going to say it's discontinuous at A. Okay, so having said that, let's look at this first example. And in this first example, we want to identify all the x values in the interval from 0 to 7 at which the function is not continuous. Now notice this is an open interval, so we want the points between 0 and 7, where the function is discontinuous. Now, we could go back and look at the definition of continuity to figure this out, but I'm going to let you in on a little secret. You can think of continuity in a very intuitive way. Continuity at a point in an intuitive way. In order for a function to be continuous at a point, you just need to be able to draw the graph of the function without lifting up your pencil at that point. So for example, when x is 4, this function is continuous at x equals 4 because I can draw the function, the graph of the function at x equals 4 without lifting up my pencil. And so for that reason, the function's continuous at x equals 4. But notice over here, I can draw this side of the function, but then I'd have to lift up my pencil to draw this side of the function. And so I have to lift up my pencil right when x is equal to 1, and so that's where you have a discontinuity. So this function's discontinuous at 1. It's also discontinuous at 2 because I'd have to lift up my pencil to draw this point right at 2. And then it's also discontinuous at 3 because I have to lift up my pencil to draw this point. And then at 5 because I'd have to lift up my pencil to go across this asymptote. And then that's it. So it looks like, at least intuitively, it's discontinuous at 1, 2, 3, and 5. Now, I do want to go back and look at the definition of continuity at a point to try to figure out why these are discontinuous. So let's start with 1. What is it about this that makes it discontinuous? Apparently, one of these three conditions, at least one of these three conditions, is not being satisfied. So let's try to figure out which one. All right, so the first condition is f needs to be defined at A. So f of 1, well, f of 1 is not defined here. There is no y value when x is 1. So that's the problem, or at least one problem, right? This does not satisfy the first condition of continuity at a point. Okay, what about at 2? All right, f of 2 is defined. F of 2 is equal to 3, so it's defined. So the first condition's okay. The limit needs to exist as you approach 2 from both sides. Okay, so if you approach from the right-hand side, the y value that you're getting closer to looks to be 1. And if you approach from the left-hand side, you're also approaching a y value of 1. And so the two-sided limit as x approaches 2 is 1 in this case. So that limit exists. So condition 2 is okay, but notice that they're not equal. The limit is 1, and f evaluated at 2 is 3. So the problem here is the third condition is not being satisfied. Okay, what about the discontinuity at 3? All right, f of 3 is defined, right? It's equal to 1. Okay, what about the limit as you approach 3? All right, from the right-hand side of 3, the y value that you're getting closer to is 1. And from the left-hand side of 3, the y value that you're getting closer to appears to be 2. So this limit doesn't exist. The two-sided limit doesn't exist as you approach 3. And so the second condition is not satisfied. Okay, because the limit needs to exist as x approaches 3. And it doesn't. Okay, what about at 5? There's a discontinuity at 5, but why? Well, let's see. What's f evaluated at 5? Well, it doesn't exist, right? There's no ordered pair at x equals 5. There's actually an asymptote here, but there's no ordered pair here. And so the first condition is not being satisfied. Okay? Okay, so that's just a quick introduction to continuity at a point. Later on in some other videos, we'll talk more about continuity at a point, and then we'll talk about continuity on an interval. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.